would like to make some announcements just related to the club in general. The first thing is that we are not going to have November and December meetings. Just give you a heads up on that, because the November one falls the day after Thanksgiving, and similar problem for December. But we will have an October meeting, and I'm going to talk about that in a second. The next thing is I wanted to remind you all that at least while the weather stays relatively warm, our fearless leader, Dick Larder, will be in the observatory pretty much every clear night as soon as it gets dark, and he's usually there for, what, about an hour, Dick? And those of you who have managed to be out walking at that time of night and stopped by, you know that he will show you some pretty amazing things. The next thing I wanted to mention is that there's a program that NASA sponsors called the International Observe the Moon Night, and I think it's October 4th. It's a Saturday, and we are not doing any major special program or anything, but Dick says if you come out, he'll try and show you the moon through the telescope. So keep that in mind. Another thing is that right now there's about 9 different comets that are approaching, or whatever, our solar system, and right now we don't have the ability to see them. They're not close enough, or they're in the wrong location for our telescope. But as we get into October, we expect we'll be able to see a few more of those. So Dick says that when he is comfortable, he can actually see those. We'll send out an email to all of you saying, stop by if you want to see the comet. So there's that, and then I need to find the description of John's talk next month. So John Mignano, who many of you know on our steering committee, is giving a talk in October, and he's going to be covering what you can see in the fall sky, like Cygnus and Sagittarius, and a little bit about the Lyra system, and he's going to highlight some kind of interesting things that maybe you can't see with your naked eye, but you could see through the telescope. So just to kind of give you almost a preview of the coming attractions in October, he'll be talking about that. And he's also going to be talking about a particular, I don't want to call it what it really is, because he wants it to be a surprise, but but it's kind of a recently discovered, almost looks like a miniature solar system with a star and planets and so on. And it's getting a lot of interest from various people who have control over the really big telescopes, but John thinks that we can get some pictures with our telescope maybe that he would show. Oh, now he's shaking his head, no. Okay, no, maybe not. But anyway, he'll talk about it because it's an interesting, it's almost like our solar system on a minor scale, and they're able to actually see things that you wouldn't expect them to be able to see now that we have so many fancy telescopes in the world. So that's pretty much the news, a part of the thing. And next I would like to introduce Janice, but before I want to do that, I want to thank Dot Bishop, who's an SRC resident, who not only had Janice, this is her daughter, but also brought her to our attention and helped me figure out how to convince Janice to come and talk to us. So thank you, Dot, we appreciate that. And then I would just like to introduce Janice. Most of you have already read the blurb that Dick sent out, so you know that she's award-winning and she's published over 150 papers, and she's a geologist primarily by training, but with a huge interest in planetary geology and astronomy. She's pretty much a little bit of all of those, which I think is becoming more common. So anyway, you don't want to hear me talk anymore. Janice.
Well, thank you, Julie, and I'm happy to be here and see so many faces I recognize. I grew up in Livermore, as some of you may know from discussions with Dot, and I know some of you from community activities like the track team or cross country or band activities, so it's great to be part of this community today. So I'm going to talk about Mars in general, but specifically about minerals on Mars, and how we identify minerals and what they tell some of the highlights. First, I'm going to talk a little bit about the SETI Institute. What is that? That's my employer. I don't work for NASA. And then a little bit about Mars and missions, and then what is remote sensing and how do we use that, and then analog sites, and then how we use all of this to determine the past, kind of being a detective to try to figure out what happened in the past on other planets like Mars, and what that might mean about life, for example, or other interesting geochemistry. So I see trying to figure out all this, it's kind of like looking at a puzzle, and I love puzzles. So we always get some data, but not always the same data from different missions, and trying to combine as much information as we can, so from the orbital missions around planets and the surface missions like rovers, and then looking at terrestrial sites. And so far we have samples returned from the moon, but we don't have any samples returned from Mars, but we do have meteorites. So we use all the info we can, and we try to put it together to blend that. So briefly, I'm going to step back. I don't work for NASA. I work for the SETI Institute. We're a nonprofit research institute, and we do a lot of cool things. And our mission is to lead the quest to understand the origin and prevalence of life and intelligence in the universe. And some of you I know are aware of this. And Jean went to our ice cream social last weekend, so those happen periodically, and everyone's welcome. The Institute started about 30, 40 years ago with the radio dish effort to listen to what's going on. It was part of NASA Ames, and then Congress decided it shouldn't be funded by NASA, so they started the SETI Institute. And now we have several different areas. We have astrobiology, trying to understand how life evolved. And then we have astrophysics, looking at stars and formations far away. And planetary exploration, which is what I lead at our, we have chairs for all these different areas, so looking at Mars and asteroids and Jupiter or Pluto, different bodies in our solar system. And we also have exoplanet detection, so looking at the planets around stars to see if they could have potentially supported life. So then this all fits together in the Drake equation. So Frank Drake is one of our founders, and he was the Dean of Science at UC Santa Cruz. Probably some of you been to Santa Cruz or were even faculty or students there. And so all of these equations, this equation has a lot of factors in it, and together we're trying to constrain or guesstimate what the probability is of finding intelligent life. So the scientists at the Institute work on one part of this. So either how many stars have planets, or the one I'm involved in is the number of planets that have an environment that could support life. So Mars is one of those, and so we're trying to characterize Mars for one of those. And one of the equation, the variable L on the end, I think is interesting because it's the length of time that a civilization was able to communicate. And so on our planet Earth, it took us 4.5 million years to get to the point where we could be sending radio or TV communications that somebody might be able to pick up. And who knows how long we're going to have intelligent life on our planet, you know? It might not be forever. And so when we're trying to communicate with other planets or solar systems, we have to think about that long time scale. And are we catching them at the right time? Not just did life ever evolve? So moving on to Mars then. There we go. So Mars is located here, and probably a lot of you hear about Mars in the news, but just as a refresher, compared to our home planet Earth and the moon, Mars is kind of in between. It's about half the size of Earth and about double the size of the moon. And Mars has 2 moons of its own. And when you look at the distance from the sun, instead of 1 astronomical unit we have for Earth, Mars is 1.5 approximately. And the period of orbit, instead of our 365.25 days, is 687, so a few extra days. And some of you who pay attention to Mars missions, you may have noticed about every 2 years they send something there, and it's a whole orbital dynamics thing. We do have some more chairs on the side if you want to. Yeah, no problem. So when we're launching planets to Mars, we want to get there in the shortest time possible. So usually we launch before we're at that place where we pass, and then land a little after. So we're shortening that time as much as possible. And if we look at the density here, it's a little less, not quite as little as the moon, but for anybody, you might have seen the astronauts on the moon and they're kind of bouncing around like they're weightless. Well, on Mars, it would have a similar effect, but not quite as much. So you would way less than here, but not quite not quite as much change as on the moon. And our planet's atmosphere is primarily nitrogen. On Mars, it's primarily CO2. So it's a big difference, and it's much thinner. So instead of 1 atmosphere, it's 1 to 9, or 1 bar, it's 1 to 9 millibars, so it's much thinner. And Mars has a North Pole and a South Pole, kind of like our planet, and it has water ice and CO2 ice. So Mars in general is much colder, and there are dust storms. So Hubble Space Telescope has taken images, and this is a less dusty view, but when the dust storms are really going, all you see is this red dust covering the whole planet. So when we think about Mars, at the beginning of time, so about 4.5 billion years ago, we think there was liquid water, at least periodically, and that might have enabled a lot of chemistry. And then over time, the planet kind of dried out, and now it's like a dusty, cold desert. But we see these impact craters that are like road cuts. So here, when a tractor's digging a road and you drive by and you can see the interesting rocks in those road cuts. Well, we don't have that on Mars. Instead, we have craters. So we use whatever we can get. And so where these impact craters have come and dug a hole and thrown out the debris, then we can see the rocks from underneath. And that's one way we can use to try to see the rocks from the past. And so there have been a number of missions going to Mars since the 70s. The Viking landers in the 70s, and then there was a gap for about 20 years before Pathfinder, and then we've had more recent ones since then. And this is a map of Mars. It's a topography map, so the low things are dark blue and the high things are sort of reds and then browns and whites. So there's some mountains, and there's a giant canyon, much bigger than our Grand Canyon, called Valles Marineris. And something you can notice, the southern part is a higher elevation, and the northern part is a lower elevation. And you don't see as many features. Like here you see all these impact craters. So some people think there was an ocean in the north, and there might have been. It's hard to say for sure, but it's very dusty now. And so it's hard to see the surface with orbiters, because the orbiters are taking pictures, and if it's covered by dust, then you can't see what's below the dust. So this is Pathfinder, one of the cute little robots that was set up in Sojourner rover on the Pathfinder mission in 1997. And that spawned a whole bunch more rovers. Each time they got a little bigger and a little better with more instruments, bigger solar panels, bigger cameras. And sometimes things go wrong, and sometimes you can use the mistakes to your advantage. And that happened with the Spirit rover. So one of the 6 wheels kind of got stuck and it was getting dragged along. And then they'd been going on this one area, and they thought, okay, let's turn around and take a picture of where we just were. And they saw, what is all this white and yellow stuff? What is that? And because the wheel was lame and got stuck, it dug a trough through the dust, and they're like, oh wow, we're gonna go back and look at that. So they went back and they took pictures with all their cameras, and were able to detect some high sulfur and phosphorus and silica regions that they didn't know were there because they just drove across and saw the dust. So that was kind of cool. And the mission I've been most involved with is called CRISM. It's Compact Reconnaissance Imaging Spectrometer for Mars on the Mars Reconnaissance Orbiter. It's a mouthful, but what they did was they had a context imager sort of in blue, and then Prism in the red patch, and then HiRise in the orange. So the HiRise is kind of like these satellites on Earth that are taking pictures of your driveway or your car or your tree, and we can see a meter or better on Mars, which I think is phenomenal to see that. And that's in 3 colors. And then the Prism spectrometer that I work with has 544 channels, so a lot of colors, a lot of channels. And we combine then these instruments on the orbiter to try to interpret what the rocks are made of. And also looking at things like from the Viking days, people thought this was Elvis on Mars or some kind of a face. And so when the orbiters get better, the cameras get better, and you get better pictures, you can see, oh, well, it's an interesting kind of mountain, but it's really not Elvis. And so this spectrometer that I work with then, it takes a picture, and then each little pixel, each spot in the image has all of these data points, so these 544 channels. And so for each little pixel, we get these wiggles, and these tell us it's like a spectral fingerprint. So for every mineral, there's a different kind of a fingerprint that we can see. And so how this works, the sun acts as a source, a light source. In the lab, we have all kinds of lamps, but the sun shines on a surface. It can be a rock, a table, a road, your hand, whatever. And then the light can be absorbed by that thing, and it can be reflected off. And so the light that's reflected is captured by the camera, and then sends back those wiggles that we interpret in the lab. And so what is a mineral? A mineral is composed of atoms, and they're arranged into certain patterns. And so some of you might have heard of olivine or gypsum or hematite or clays. And they each have a different arrangement or pattern of these atoms. And you can see like a lot of these make necklaces. Sometimes I wear hematite when I do these talks, but hematite or lepidoprosite, or there are a bunch of these really cool kinds of minerals that have different colors. And so they all have a different crystal structure. And so we use the crystal structure for detecting them. So each of these bonds in here has vibrations, and they're either stretching symmetrically or asymmetrically. Probably at the gym, your trainer's telling you, we're gonna do some asymmetric stretching today, or whatever. So the molecules do this too. And so by using these different stretching vibration modes, then we get different bands. And so we use these bands in order to identify the minerals. And we also get colors. So the iron or the chromium or the vanadium or the whatever it is, these metals all have an excitation to a higher level, and that is what gives the color. And so they each have a slightly different color. And even iron-bearing minerals here have different colors depending on the structure of the mineral and how those atoms are arranged in the crystal structure. And so these are the kind of spectra we see for these different colors. And this is in the visible region, and of course there are wavelengths, longer wavelengths and shorter wavelengths, but this visible region is used for looking at differences in iron. These are the colors that our eyes see, the red, green, and blue here. So our eyes are designed to look at these 3 colors, and we're very good detectors. Each of us is a spectrometer, and we use those, our brain takes those 3 colors and we combine them when we're looking at things, and it tells us what colors we see. So these instruments that NASA produces, they also are collecting channels, whether it's 3 or 5 or 500, and they're processing them into these wiggly lines that we interpret then. And so we plot them then often in these different colors. We pick 3 bands at a time and plot them into red, green, and blue, and then we can express different kinds of minerals in these different colors. And this is a map of Mars, and it just shows a lot of the alteration minerals, things like phyllosilicates or clays, and silica, chlorides, carbonates, sulfates. So when you look at this southern part of Mars that's exposed with all the impact craters, you see all kinds of cool things. So all these different minerals tell us that chemistry was active at one point on Mars. there's plenty of water, and a lot of things changed and formed these alteration minerals that we have all over Earth. Only here we have roads and trees and people and garbage, and it's covering a lot of the cool rocks. So, and we use these images then from CRISM to try to look for outcrops. So this is from Gale Crater, which the Curiosity rover is visiting. And the Curiosity rover has even more instruments on it than the past ones, and it's climbing up this mountain in the middle of the crater right now and looking at these exposures. And then at Jezero Crater, we also can look from orbit and see differences in the clays and the other minerals present, and that's usually how we select the landing sites. The people doing my kind of job are looking from orbit and trying to guide where are the really coolest, interesting spots that we need to go send a rover to find out more information. And so some of you have followed the news since 2021 when Perseverance landed. Oops, I spelled that wrong. Perseverance with an A. And here's the helicopter Ingenuity, and there's some cool little videos online if you want to watch Ingenuity fly. They didn't know if a helicopter could fly on Mars because the atmosphere is so thin. So this was like an engineering test, and it worked, so that's good. And how do we then interpret all this stuff that we see from orbit or from the rovers? So one way is to go look at analog sites, and I think many of you here in this room like to travel, so you've probably seen a number of these sites too. So this is in Iceland, and it's volcanic, and their alteration of the volcanic material here is really helpful for understanding alteration of volcanic material on Mars or other bodies. And going back to the little puzzle of looking at analogs and trying to compare that to surface missions and orbital data and meteorites. So these are some of the sites I've been to. Santorini we talked about a little bit before. Iceland has volcanoes that erupted through the ice, so that's a little different kind of alteration. And in Italy and Canary Islands, the Hawaiian Islands, so a lot of different places have islands where there are more rocks than people, so that it's easier to see the rocks if you don't have a lot of vegetation or people around. And so this is one place in Iceland where we went, and we were looking at the kinds of clays that form in these rocks. And in this case, it's a little bit different because it's hydrothermal, but under ice, under the glacier. But we're still seeing a lot of similar kinds of clays, but it forms more like a rock. So trying to compare what we see from rainier environments or drier environments or subglacial environments helps us understand what we might expect on Mars. So, and this is the kind of data. So when we go in the field, we take sieves and magnets and try to understand a little bit what we can there, and we bring the samples back and we measure more properties in the lab. And this is another place, a hydrothermal spring, where we're looking at the alteration through rain down the sides of these volcanoes. This is a hot spring, and there's also some of this forming on the sides. And this is an iron mineral called ferrihydrite, which is one of the first iron oxides to form and probably very present on Mars. And this is then from Santorini. So we were looking at some of the hydrothermal sites. So they're little volcanic cones spewing out some sulfuric acid, and all the rocks around then get altered. And so we're looking at the kinds of minerals that form. So we can see hydrothermally high temperature minerals versus in some places far away from the cinder cones, we see slower alteration in different minerals that form. And this near Naples in Italy, they have a campground inside this caldera, and a French friend of mine organized, and we actually camped there. And it was kind of this fun destination. There were a bunch of Germans who camped there in their like RVs, which seems totally weird. And now it's gotten more active, so they've closed it, so no one goes. So I'm very happy that we got in when we did. And we were looking at a lot of these sulfur vents and the minerals that formed there. And this is on the Big Island of Hawaii, near Kilauea. And this site actually, the caldera collapsed. So we went there with some professors from Davis who they used to take their students out for field trips, and they found this site, and then we went there a couple times in 2004 and 2006, and then I think in 2018 it got active, and we went back in 2021, and this whole side is gone. It just collapsed right in. So they're evolving landscapes, and this again, then once you bring the samples back, you can measure them with more things in line using SEM to look at the relationship between the grains really zoomed in and doing moss power. This is what I do with my friend Darby Dyer, who you went to college with, and then the spectroscopy that we actually use for the orbiters. And this is from Haleakala. Haleakala on Maui is my favorite volcano. This is the one I like the best. And this was my first field trip, and Mom went on this too, Dorothy Bishop. I was a grad student at Brown at the time, and we were visiting relatives in Hawaii, in Honolulu, and I said, oh, I really want to go over to Maui. And so Mom and my brother Bob and I flew over for a couple days and hiked down, so it's 3,000 meters high, and we hiked down to 1,600 meters and then back up. And so it's hard going back. And going down, it seems like, oh, this is cool. Going back up, I've forgotten how many feet that is, but I guess 9,000 or 10,000 or something. So it's not the highest place, but it's hard after a longer day, and you can ask Mom what she thought. We dragged her with us. And so back to our puzzle then, we try to put together this information to understand Mars. And what my group does then is look at the different kinds of minerals that we're interested in, that we found on Mars, and what kind of environments they form in order to understand those. And if we look at the orbital data again, we have these small patches that in these views, the red and the blue are the very common clays that we see that are called smectite clays. And all of you who've lived in California a long time, these are the clays that make your house shift. So like for us at our house, the gate on the side with our orange tree gets stuck right about now, at the end of summer when it's really dry, and it's really hard because the ground shifted and it's really hard. And so there's the periods of time where you see in your yard the ground is very hard because of these clays expand and contract with water. So those are very common on Mars. But then we have the stuff that I've marked in green in both of these. They're unique things like small outcrops of weird clays or sulfates, and those are the things we're trying to understand, not the stuff that's common everywhere, because that we kind of get that part, but so we're working on these weird small things. So looking at which kinds of environments, like on the island of Kauai, it's a little more rainy, and so they get some of these clays that, like kaolinite or halloysite, that form more in rainy environments. And so maybe it was the wet, dry cycling environment, and then it was rainy for a while, and they got these little pockets of this kaolinite or halloysite, and then it went back to the wet, dry cycling. So it's kind of fun to be a detective and try to take the clues that we have today and work back in time. And so in one way, the Perseverance rover at Jezero Crater is trying to figure this out now. So this is the marking for Jezero Crater, and any of these craters that are very old on Mars were probably paleolakes, and there are people whose job it is to look at the morphology. So they look at the shapes of features on the surface, deltas or valley networks. And one of the reasons that we decided to send the rover to Jezero Crater is because the mineralogy looks cool from orbit, and also it has these delta-like features. And so what we wanted to do was then go look in this delta and see if we see minerals that are different than we see on the surface, and do we see any signs of life, and should we bring those samples back to explore? And so there were a bunch of papers, well, 2 papers in Nature a couple weeks ago, which you might have heard, and I was asked to write a commentary. So one of those papers is a very short one that I wrote with my first graduate student, Mario Prente from Stanford, and he does this amazing mineral mapping with CRISM. And so this is an orbital view of the minerals, color-coded on top of some high resolution surface views. And so the rover landed out here, and then it drove around a little bit on this yellow path. And as it drove around, when it got to this place near this sort of valley system, it found some interesting minerals, and that's what my colleague Joel Hurwitz was speaking about. And we're going to zoom in this area. So Joel published a paper in Nature after studying this quite a bit, and found some unique rocks in this area. And this region that he's looking at is a mudstone, and I don't know how well you can see. Does this look reddish? This should look kind of reddish right here and kind of whitish. So the way minerals combine, it's kind of like building Lego projects at home. It's like if you normally build kind of blue and red together, and that's your pattern, and then suddenly there's some like green ones or orange ones, and you're like, oh, well, how do we get those in there? So when we're looking at some of these places, we see some weird minerals that aren't normally found together, and so that's what they found. And I'm for our sort of clarification paper, I marked some of the places that they're calling poppy seeds and leopard spots. So the Mars rover teams, they like to have these funny names. I don't know, sometimes you can see kind of what they're talking about, and sometimes it's a little weird, but I think in this case, these do kind of look like poppy seeds. So you see this reddish mudstone, which has clays and iron oxides and kind of normal stuff. And then these little black spots. And at first they just looked like little black spots, but then the rover went over and started analyzing them with their tools, and they found that they were high in phosphorus. And that's unusual. And Mars in general has higher phosphorus compared to Earth, just in the regular soil. And they noticed that the black spots were not only higher in phosphorus, but also iron. And so it was an iron phosphorus something. And so they started analyzing this with more minerals, and then more instruments, and then these instruments told them that it's likely an iron phosphorus mineral called vivianite. And the interesting thing is that vivianite has reduced iron. So you have oxidized iron with these little black specks of reduced iron, and these oxidation reduction reactions are kind of a weird thing to see on Mars. So on Earth, it happens all the time. You're like, oh yeah, there's some microbes in there. Okay, not a big deal. We have tons of microbes here. But on Mars, we haven't seen any evidence of microbes yet. And so the team was like, wow, what did we find? Let's go look some more. And so then they found these leopard spots, and these have white and black together. So the little whitish appearing spots here are a kind of sulfide. And so normally there's sulfate, which is an oxidized form of the sulfur, and so the sulfide is a reduced form. So again, it's some kind of reduction reaction going on. And then they found organics in this region, and they noticed that the places that had the poppy seeds and the leopard spots had less of the organics than the places that didn't have those. So they thought, oh, well, maybe the organics are reacting to reduce the iron, which I've done in the lab for other things just out of curiosity, and that does happen. So if you start with ferrihydrite, which you can collect in Iceland, and put in some amino acids or some sugar and heat it up a little bit, then you either get hematite or you get magnetite, depending on what atmosphere you put in there. So it's kind of cool to see that that can happen. And they don't believe that this was a high temperature reaction just because of the fabric of the rocks. And so they think this could be a potential biosignature. But we also have a lot of time on Mars, so most of the experiments we scientists do in the lab, we kind of want to know the answers, so you heat it up to make it go faster so you can get an answer today or next week or in a month, and you don't want to wait 100,000 years to know the answers. So on Mars, though, we have a lot of time, and so these reactions could have taken a very long time, 10,000 years or a million years. They could have gone on for a long time, and so we don't know if they're inorganic, Or if because there could be some weird metals in there that could be reducing these, or they could be organic because of a reaction with the organic materials they're seeing, but not biologic. Or there could be microbes there. So it could be a lot of things. And I think maybe besides the question of is there life or not, the question is, are we seeing evolution of some of these organic materials? Because we know from comets that distribute organics everywhere, and asteroids, a lot of asteroids have organics. And so how do we get from this organic material that's thrown around our planetary system, how do we get that to amino acids that formed life on our planet? And did that happen on other planets? So maybe these kinds of reactions are showing us, oh yes, that same prebiotic chemistry is happening on Mars, or, well, maybe not today, maybe it happened 3 billion years ago or 4 billion years ago. So that might have happened, at the same time life was happening here. So Mars was chemically pretty active early on, and then it kind of cooled down and froze. So in some ways, looking at Mars, we get a glimpse into our own past, maybe. We're seeing what might have happened on Earth as life was evolving here. So I think this opens more questions than answers in this case, and we hope that the sample return mission will be reinstated. So our current administration canceled that, along with other missions, but hopefully, they have to reevaluate finances, and hopefully they'll decide this is an important mission and reinstate that, and we'll get those samples back. So I think a lot of experiments we can do in the lab here are able to tell us more information. So we can do sulfur isotope analyses, and that'll tell us the origin, were microbes involved or not, and that should help us. And we can look at TEM or really zoomed in microprobe views to see the interactions on a really molecular scale between these. So that should be cool. So that was what I wanted to talk about today, and I'm happy to answer questions or talk about related topics if anybody has questions or other things they want to talk about today.
How did they get the sample back? Do you send that in the sample? Send it on the spaceship?
It's complicated, yeah. So the samples, the Perseverance rover has these little sample caching devices. They're about like the size of a finger, but it's like a water bottle. It's insulated. And so I think there are 36 of these, and they collected 10 and they dropped them in one place in case the rover dies and gets stuck. And now the team's decided to drive the rover. They've made it outside the crater, and they've turned around and they're heading back in. So I'm not sure if they're going to the same place where the other cache is or to another place, but they're scouting out where is like a safe, good place. So they might be going back to this landing site, somewhere where it's easy to land. And so the original plan was the Europeans were building a little like rover thingy. So there would be a mission to drop off this rover, and the rover would drive around and get the cache, and then it would have like a hook, and then something else would come by and catch it and fly home. But they're modifying the plan, so I don't know what the current plan is, and I don't think anyone knows. So the NASA's looking for a cheaper option, so we'll see what ends up happening. But it's not so easy. So whenever you send a mission that has to come back, you have to bring your fuel with you if you're stopping. So if it's just a rover or lander, you fly the thing there, it drops in its parachute or whatever and unfolds and then drives around and it stays. But if you want to try to bring something back, so they're thinking about a way to like fly by and not actually stop, but to fly by and capture it and come back. That might reduce the amount of, that way they wouldn't have to land and then have fuel to somehow take off again. But yeah, so there are a whole bunch of engineers. So all this work takes scientists and engineers, and it takes all kinds of planners to figure this out. So it's a lot of people with a lot of different backgrounds. Yeah.
What does SETI stand for?
Search for Extraterrestrial Intelligence. Yeah, so it started mostly with these radio dishes listening to messages, and then it broadened to right now, I think that's about 5% of the institute, so more of us are looking for exoplanets or looking at Mars or Europa. There's another big NASA European mission called Europa Clipper going there in, I think, the near future. And they have a spectrometer called MISE that's somewhat similar to the CRISM that I worked on, where it's going to fly around and map the minerals and hopefully tell them what kind of interesting things are present.
Have there been other planets, moons, where you've seen poppy seeds and leopard spots, or just on Mars?
Well, other places have some really cool things, not exactly these, but Ceres, for example. Ceres is a huge asteroid that's called kind of a dwarf planet often. And Ceres has ammonia connected to the clays, which is really interesting. So ammonia is, that NH4 is part of amino acids. So that implies evolved chemistry, and it's embedded in the clays. And Ceres also has carbonates, and it also has organics. And so it's a really interesting place. And these two asteroids that have had samples returned, so they're called Bennu and Ryugu. So Ryugu is from the Japanese Hayabusa mission, and Bennu is from the US, the NASA OSIRIS-REx mission. They're related, not exactly, they're C-type asteroids, but I think Ceres is a CM or some kind of a C, and Bennu and Ryugu are a CI, I think. So there's slight variations, but they all have these ammonia clays, and they all have carbonates, and the pieces from Bennu were big enough. They've done all kinds of really awesome microprobe work, and they found weird phosphates there. So not quite these same ones. So the ones on Mars, these are iron phosphates with reduced iron, and the ones that are found in Bennu, I think they're magnesium calcium phosphates, which are kind of weird. So calcium phosphate is apatite, so you might have heard of apatite as a mineral, but in any case, they're different kinds of phosphates. But again, phosphates are necessary for, it's one of those carbon, nitrogen, oxygen, phosphorus are those sort of essential for life elements. So most of the others we found, the carbon, oxygen, nitrogen, but the phosphorus, when we find that, that's kind of a little less common, so it's more notable.
Thank you.
Mm-hmm.
So there was a movie with Jodie Foster about Jill Carter a long time ago.
Contact, yeah. And Carl Sagan wrote the book kind of about himself, but also a little bit about Jill Tarter. And so it was kind of, and it was a new character. Wasn't just about Jill, but a lot of the characters in the movie and in the book were some of the original people. There was a blind scientist, for example, on her team who was a real character in our institute back then. Yeah. Do you want to facilitate questions, or should I don't know if there, it seems like there are a lot. Do we need a mechanism of, I don't know.
I wish we had a second microphone, or just point.
Okay. Okay, all right, well, let's start towards the front here and then move back.
I have two questions. So I could be wrong, but I think I had a friend, and this was probably at least 25 years ago, and on his computer he was doing stuff that, was there ever a time when just normal people that had computers were doing things for SETI, looking for indications of life elsewhere? Or was that something completely different?
There was a SETI at Home project, and I think it was in the 80s and 90s, and a lot of people could let their computer work in the downtime. And I think that was from a SETI group at UC Berkeley, and they were affiliated with the SETI Institute, but the idea, I think, came from Berkeley.
Okay. My other question, and this is probably why I don't know very much about physical science, and I did take one physics course, and my physics teacher told me to take a philosophy of science class. But we're presupposing all our knowledge, like, different wavelengths and how you detect minerals and everything on this. How do we know? I mean, it seems to me that it could be something completely different, that we're just like out of our realm of knowledge, that's just so far away. I mean, is that just totally off the wall? Because,
Well, especially regarding life, we really don't know how life evolved here, and we don't know all the potential forms of life that could be possible. And when I was an early fellow at NASA Ames, we were in the early 2000s, we were trying to figure out, how do we define life? What is astrobiology? And defining, what that is. And so I actually heard a talk on NPR driving over here today. There's a professor at Stanford, Paula Weeman, I think, or something like that, and she's looking at proteins in simple life to try to define better what defines life here so that we can better define life somewhere else. And so, yeah, we don't know that. But in terms of the chemistry and the minerals, I think so far everything we found is based on the same elements we have here on Earth. So I think that's pretty standard. So like hydrogen, helium start, and then as they have fusion, they form other elements. But all the elements we see here are pretty much the elements we see anywhere we've looked. So I think the chemistry, physics is pretty universal.
Thank you.
Maybe we can go around there.
I don't know if I could maybe pass this down to Lynn.
Yeah, I'm just curious, does Jill Tarter still work there, or is her work continuing?
She's retired and she's on our board of trustees, and I just got an email from her last week about something. So she comes to some high level meetings, and sometimes she chimes in with an answer, but she's more retired than not, but she does still listen and contribute sometimes. So yeah, it's great when she does appear. We're happy to hear from her again.
So one of your early slides implied that there was water on Mars at one time. Is there any hypothesis on why the water disappeared? Was there an atmosphere? Why did the atmosphere disappear?
Oh, there are lots of hypotheses and lots of ideas, and we don't know which one is the right one. This is actually one of those big discussions we often have, because the geologists are looking and they're seeing like these huge, like the giant canyon. Valles Marineris was carved out of water somehow, so there must have been a ton of water. And then even like for Jezero Crater, there's this huge delta. So all this material there, it all got pushed in, and then the people with more chemistry side, like me, then we're looking at the minerals. It's like, well, these minerals need water to form, so there had to have been liquid water. So if the water was fast moving and was cold and didn't stick around very long, then we might see these deltas and valley networks and the carving of the troughs. But if the water is a little warmer and it stuck around for a while, then we see clays and carbonates and some of these interesting minerals that need warmer water. So we definitely had both, but still, how long did they exist? So and the challenge is that we now have a very thin atmosphere, and so the modelers who were looking at the atmosphere are thinking, well, okay, we could have had hydrogen or methane, or they're trying to figure out how could we have gotten a thicker atmosphere. And so there's sort of a disconnect, because they're like, we only see cold and dry, but we know there was water, and we know there was a lot of water, and we know there was some warm water. And so one of the things I proposed a few years ago for a paper in 2018 was we had shorter episodes of warm water, that it wasn't, because some people said, oh, it was warm and wet for like, I don't know, 500 million years, but it may have only been warm and wet for 1 million years or 100,000 years. In cycles. Short, yeah. And we don't really know the answer, but a more recent study from Gale Crater, where the one rover Curiosity is, they found an interesting combination of carbonate and iron carbonate called siderite, which we don't usually see. We usually see magnesium-rich carbonates, and so they started thinking about this, and then I built sort of on their idea. And so this idea that we came up with is that magnesium clays and siderite form near the surface, but maybe below the surface. And so it didn't need, there was water, but it wasn't on the surface, so it didn't need to have a thick atmosphere. But then as the volcanism continued and put sulfates into the brine and into the flow, it altered these, and they traded cations, because now we see more iron-rich clays and more magnesium-rich carbonates, and it also made sulfates and some of the iron oxides we see. And in the process of all of that, it chewed up tons of carbonate and spewed it all in the atmosphere, and that made a thick atmosphere that enabled the water, liquid water on the surface. So maybe we're right, maybe not, but that was from Science in April. So I can send some links to these papers to Julie, and she can post them if you want to read the nitty-gritty. But the answer is we don't know, and we have lots of ideas, and we're encouraging the young people to think of more ideas so that we can get closer to understanding this.
Pass that to Candy. You?
So you said all the minerals that you found on Mars, you also find here on the Earth. Is there anything that you've found up there that's not identifiable?
Well, there actually is something that we haven't found on Earth yet, only in the lab. And, well, there's two things. So one, some Canadian researchers about a decade ago, they brought home a magnesium sulfate they were working on over Christmas break. And it was so cold that year in Canada that the stuff got really cold and formed a new mineral. And then they were looking at the data like, oh, we have that here on Mars, wow. So they named it meridianite. And then a group I've been working on, a different project than the other ones, we had these weird bands at 2.23 microns that we couldn't explain. They didn't match any of our minerals, they didn't match any mixtures, and we thought, oh, well, it's like alteration of something in a weird environment. And then we started doing experiments, and we found out that if you dehydrate certain sulfates, they form this hydroxide, so an OH instead of a water in the crystal structure, and it distorts it, and we get this weird band at 2.23 microns. And so in this case, we think we found a new mineral, and I've been working on this, and we just published that in August in Nature, and it's really exciting study, but we can't name it until we find it on Earth. And so in this case, we made it in the lab, and we found it on Mars, and everyone kind of agrees that this is what it is. It's not like I have this opinion and everybody thinks I'm crazy. Everybody says, yep, that's it. But we can't name it until we find it. So I guess we'll have to go find it on Earth somewhere. Maybe we'll be able to do that, and then we get to name this crazy new thing.
Meteorite.
Yeah, maybe that's right. Yeah.
Maybe a meteorite from Mars landed here.
And would have that mineral, and then it's on Earth, so then they can name it.
Yeah, if we can find it somewhere.
Seriously, we've learned a lot from meteorites.
We have found a lot of meteorites.
How do you know the meteorites are from Mars? Do they land on Earth or by meteorite? How do you know it's from Mars?
Well, there are a lot of ways they can tell, but the ringer is the oxygen isotope measurements. So each element has different isotopes, and the oxygen can be, I think, 16, 17, 18, and they do a ratio of 16, 18, 17 to 18, and Earth has a place where it always is, and the moon has a place where it always is, and Mars has a place where it is. So all Martian meteorites have this same spot. So before they figured that out, in like the 40s, 50s, 60s, they were guessing, they knew they were meteorites because they have a fusion crust. It's like, gets burned up when it comes through. And then based on the types of minerals inside. But they were never really sure until they figured out this story with the oxygen isotopes. So that's kind of cool, yeah.
I thought I saw a hand on this side here. Is that you, Deb?
Yeah. I was just curious about whether you have any information about naming the sampling sites. I see Bright Angel and Masonic Temple. Do you know how they were named?
Well, it used to be totally random, and some of my friends named a rock Ginger after their cat. But now they actually have naming procedures for these. So I think they have themes, like certain regions will have one theme, and the next little region will have another theme. And besides, they name a lot of stuff, the rover teams, but also just the crater. So I've named a few things, and trying to name craters has certain rules, so there's this International Astronomical Union, I think, controls that, and so they have certain sizes of craters that can be named after people and certain sizes that can be named after cities, but the cities have to have under 100,000 population, and there are too many named after US and German and Norway or France or whatever, so they, in this naming process, they've said, well, how about try some of these other countries like, oh, I don't know, like, yeah, some of the Indonesia or some of these, and the problem is when you try to go, look, if the city has less than 100,000 people, there's nothing on the map. I mean, it's really hard, and, you know, I try to name my craters with something that has something to do with the place, like I found a city in Brazil that was near some mine that had some kind of minerals that were close to something I saw on Mars, and a lot of people just picked something they went on vacation and thought that was cool. But I did name one Druzhba, which means friendship in both Russian and Ukrainian, and I don't know if we'll ever see that, but
Good effort towards the peace.
yeah. So maybe that's a good point to stop, and thank you for the opportunity to come here today, and maybe Julie can help if there are questions we can try to answer, or you can check with Mom.
Yeah.
So.
Dot and Janice have to catch a flight, so they unfortunately have to stop, but I'm happy to stay if you have more questions. I'll do my best, and I'm really good at making stuff up if I have to. Thank you so much. John wants to talk.
Thank you, Dr. Bishop. Before Dr. Bishop leaves, you gave me a great introduction to my presentation next month.
Oh, I'm so glad. Good.
You mentioned SETI, the Search for Extraterrestrial Intelligence. You mentioned exoplanets and the Drake equation about the formula for the probability of finding intelligent life outside our solar system. And that's actually part of the highlight of my presentation, as I present information on a recently discovered star about 25 years ago that's nearby. And less than 10 years ago, they found 7 planets around that star. So there is what's called a habitable zone, and so the potential for life, and so this is getting some interest among the professional community. So thank you very much.
Yeah.
And I understand they pointed a lot of our space telescopes at it to try and get more information. Yeah.
Sounds like a good talk next
Yeah.
week. Yeah.
And I would like to ask all of you, it's good to see such a huge turnout, and I credit our speaker for that, but if you had a good time today, please tell your friends to join the Astronomy Club. And all that means is you give us your email address, and then you're on our mailing list, and you'll find out about these talks and anything interesting that's happening in the sky that we can help you find. So also the club and committee fair is on October 24th, and we'll have a table there if you want to stop by. We'll have some interesting things to look at.
Thanks, everyone.
Excuse me.